So hello, everybody. So welcome to this webinar presented by the Connecticut Power Electronics Society in partnership with the Princeton-Philly Power Electronics Consortium, as well as the Virginia Tech student branch chapter of the IEEE Power Electronics Society. So for those of you who don't know me, my name is John Noon. I'm a senior electrical engineer at Otis Elevator Company and chair of the Connecticut PELS chapter. So on behalf of the Connecticut PELS chapter, I would first like to sincerely thank you for joining the webinar presented by Mudit Khanna about how B-TRAN is revolutionizing solid state protection. Before we kick off the webinar, I'd like to give you a short introduction to PELS for those of you who may not be familiar. So PELS is a society within the IEEE, which is the largest technical professional society. From what I can see, IEEE is in 5th place behind the National Association of Realtors, though I'm not sure how that will change upcoming. The American Bar Association, American Institute of CPAs, and the American Medical Association. So not bad company. The PELS vision statement is to be the global resource that all people turn to for education, knowledge sharing, technical events, and networking in the power electronics field. The IEEE PELS core purpose is to foster power electronics technology, innovation, and excellence for the benefit of humanity. So benefits of IEEE membership include online access to all PELS-sponsored conference proceedings, including APEC and ECCE papers, as well as the listed journals. So personally, I think this is a huge benefit. Beyond access to the technical papers, there are also many avenues to get involved, focused on either technical development or more people-focused roles. I think both are excellent for professional development, depending on what you want to get out of it. Personally, I'm involved in both serving as a reviewer for APEC and ECCE for the past few years, as well as more recently as a reviewer for both the transactions on power electronics and transactions on industrial applications. Personally, I think it's important for people in industry to be involved in these functions in order to offer our perspectives, as well as to help keep ourselves up to date on the latest trends. So all of the different tracks and resources are available on the PELS website. So for example, at APEC last year, I spent some time going to different IEEE meetings and all of the different groups, such as technical committees, membership. Everybody's looking for volunteers, so you should be able to align your interests with an opportunity to give back to our profession. So to provide some more detail and context on the Connecticut chapter in particular, so we have the same or similar goals at the national level, but focused on Connecticut engineers. So part of that's through in-person events like the factory tour we had recently, but some of that is also by broadening our horizons by reaching out into the broader community and engaging nationwide, such as this event online today. So you can see a few of the events we've had so far. So as I mentioned, we're a new chapter. We hosted our kickoff event last October. Since then, we've had a few of the events listed. So this is our second ever webinar. So I appreciate you bearing with me and with some of the learning experiences, as well as we've had I think this is we've had 2 in-person events this year. So we're certainly trying to be an active and engaged chapter. So stay tuned for our next event in September timeframe after a short summer break. So in conclusion, PELS is volunteer driven and about you, the members. A spoiler is that we aren't planning to make our events restricted to only PELS or IEEE members, but I certainly think there's some benefits to membership. So if you're interested, you can use the code on the screen to get a complimentary PELS membership, regardless of your IEEE status. So with that, I would like to introduce you to our speaker. So first, I would like to thank our XCOM for all of their helping getting things up and running. So then I would like to introduce our speaker today. So Mudit received his Bachelor of Technology degree in electrical engineering from the National Institute of Technology in India in 2012, an MS degree from Virginia Tech in 2017. Mr. Khanna has spent more than a decade in semiconductor industry working on power electronic systems, power semiconductor devices, and power management ICs. He was a He was a product definition and applications manager at Analog Devices between 2017 and 2023, where he developed high power density and ASIL rated PMICs for automotive applications. Currently, he is a technical product manager at Ideal Power Inc. and is leading product development and commercialization of B-TRAN based products. He's published multiple research papers, articles, and holds more than 8 patents on B-TRAN device technology, driver design, and packaging. With that, I'd like to turn it over to Mudit for your presentation. So thank you again for being with us today. I really appreciate it.
Thank you, John. Okay. Can everyone see my screen now? I think, John, this looks good.
Yes, we can see.
Okay, perfect.
Thank you.
Okay, welcome everyone. First of all, thank you for being a part of this webinar. I hope to keep you engaged, and we want to introduce you to our new exciting technology that we've been working on here for the past few years. And B-TRAN is really a different architecture and a different switch technology that we've been pioneering, and it's a bidirectional switch. And we would want to talk about today, we'll talk about how it is helping solid state protection industry and how we are applying this switch in that application. Okay. Okay, so overall, we'll start first by giving a short introduction about the company, Ideal Power, and then we'll go on and talk about what really is B-TRAN, right? What's the device architecture and operation, and how does it compare to other bidirectional switches in the industry? We have test results and characterization results that we'll share. The architecture lends itself to a slightly different driver design because it's a unique architecture. So we'll go into the details of how we can drive a B-TRAN, and then really go into application-based questions like what are the key requirements for solid state protection circuit, and why should we use B-TRAN for that? We have some test results that we've done some good work on looking at B-TRAN and testing it in the circuit in a solid state breaker application, and then the future work and development. Okay, so Ideal Power is a public company. It's listed in NASDAQ, iPower, and it's a public startup, and it's pioneering the innovative bidirectional switch technology called B-TRAN. B-TRAN is bidirectional transistor, and we'll go into more details why that is. So B-TRAN is a disruptive semiconductor technology. It's a unique architecture that we've done first in silicon, and it can also be replicated in silicon carbide, but we've started with silicon, and we've launched a few commercial products, including discrete device, multi-chip power module, and also an intelligent power module. We have a broad patent estate. We have a lot of good IP, both from device, driver, packaging, and we have a lot more pending as well. We are an asset-light fabless company, and we are headquartered in Austin, Texas. Okay, so based on that, we'll go over what is B-TRAN and device architecture. So what is B-TRAN, right? It's a high voltage monolithic bidirectional switch. I would say it's one of industry's first monolithic bidirectional switch. And the unique advantage that we have is it's ultra low forward voltage drop. And the way we achieve that is by this unique architecture that's shown here. First of all, the die is completely symmetrical on top and bottom. So the wafer looks exactly the same from top and bottom. And that's why the performance is the same in either direction. We have four terminals total in the device, E1 and E2, B1 and B2. And we'll go into more details of how the device operates with these terminals. In addition to the ultra low voltage drop, it's bidirectional switching. So it's complete 4-quadrant operation. With low conduction losses, it's very highly efficient and reduces the cost where it significantly reduces the system cost where we need bidirectional switches. The first generation is fabricated in silicon, and it's a 1200 volt device, and that's already available to order, and we are already sampling to customers. Overall, what is new is we have a new architecture, a new switch design. We have a proprietary double-sided process, and we also have some unique innovations in our packaging technology, which allows for symmetrical heat transfer from both top and bottom side. So we have a double-sided cool package. Okay, so what is different about this architecture, and how does it enable 4-quadrant operation? To understand that, I think we can look at its closest ally, IGBT. So IGBT has been in industry for a while, and it has been the workhorse for high voltage applications till now. And obviously we have now wide bandgap devices as well. But if we look at the device architecture of an IGBT, it's a vertical device. At the bottom, there is a PN junction, and then on the top is a metal oxide gate structure, which basically controls the MOSFET, controls the IGBT. So the top side looks similar to a MOSFET, but the bottom side is actually a PN diode. So this is the collector, this is the emitter, and here is the gate. So if the current flows from collector to emitter, there is a diode followed by a channel resistance, and we use the gate to control the channel, right? Overall, so the summary is it's metal oxide that uses on and off to control the switch. We have minority carriers that basically are injected into the drift region, and hence the bipolar nature of IGBT. And there is a diode always in series with the channel resistance. And that's why we see a knee voltage in the IGBT. So there is always a 0.7 to 0.8 volt drop because of the diode. Now, if we look at B-TRAN on the same hand, E1 and E2 are our main current paths. So we flow current between E1 and E2, and B1 and B2 are our two bases that we control. This is the top side, and this is the bottom side. So if you see between E1 and E2, it's just a drift region, and there is no diode in between. So what that means is we naturally don't have that extra voltage drop of the diode that typically we see in an IGBT. Bases B1 and B2 are used to inject current into the drift region. Now, we do have minority injection, so it is also a bipolar device, but it's a controlled injection, and the injection path is different from the main current path. What that does is, first of all, it's a normally on device, because E1 and E2 itself is basically, there is no control here. You cannot stop current, it's normally on. However, we can use a cascode MOSFET to block and make it normally off, just like what we do in JFETs. We have minority carrier injection through B1 and B2. So when we inject base current, the resistance of the drift region drops significantly, and that's what gives us the ultra low conduction losses. And the diode is really in parallel with the resistance. So there is no knee voltage effect in B-TRAN. And hence, if you have very low current, you'll have low voltage drop. So how do we really implement this operation in a switching operation, right? So how do we implement a bidirectional switch? So to make it normally off, we add two low voltage cascode MOSFETs at the bottom and one at the top. Because it's bidirectional and we need to block voltage in both directions, we need two cascode MOSFETs, one at the bottom and one at the top. To turn on the device, we inject current from bases B1 and B2. So we have, and this can be controlled in whatever and the injection level basically can be controlled. So we have two injections. If it is a bidirectional operation and we wanted no dependency on the sense of the direction of the current, then we can just drive both P1 and B2 exactly the same way. So if we drive both, there is no dependency on the direction, and the driver control becomes a lot simpler. Now, to turn off the device, we turn off the cascode FET. Now, when we turn off the cascode FET, naturally these two diodes will block current in either direction. So if, for example, S1 is high voltage and S2 is low voltage, E2, the FET on the E2 to S2 will basically block any current flow from E1 to E2. On the other hand, if there is high voltage on S2 and low voltage on S1, then the MOSFET on the top side will block the current. What happens is we have to understand the operation and how the device would operate, we'll have to look at the multiple diodes that are inside the device structure. So as we see, for an example, S1 being positive and S2 being negative, there will be a voltage drop across the device and the current will stop flowing. But B2 is shorted to S2. So if S2 is low voltage, which is virtual ground in our case, the voltage E2 will continue to rise above S2. So N will become more positive than the P plus region. And you'll see a pinch off develop between these two junctions, which is very similar to how a JFET would operate. So if we take reference from the cascode JFET operation typically seen in United Silicon Carbide's JFET, this is very similar. So we have this diode that basically pinches off this whole region and creates and turns off the device. So in summary, to turn off the device, we just need to short B1 and B2 to S1 and S2 and open the cascode FETs. The voltage that appears here on E2 is a function of how much voltage we are blocking between S1 and S2. So for a 1200 volt blocking operation, we would just have about 40 volts across E2 and S2. So a 60 volt MOSFET is enough to block 1200 volts. The rest of the voltage is dropped in the drift region of the B-TRAN. Okay. So based on that, we can now look at how does this switch really perform? How does it compare to other bidirectional switches in the industry? And why do we need bidirectional switches in the industry? Like, what are the new applications and how are they doing right now? So B-TRAN offers really ultra low conduction losses compared to other bidirectional switches. So currently in the market, there are very few, I would say, monolithic bidirectional switches. Most of it are done by putting two MOSFETs back to back or two IGBTs back to back. Most of the time, these are separate dies that are co-packed together and we form a bidirectional switch. In IGBT case, we have almost 4 dies because the diode is not inbuilt in an IGBT. So we end up putting 4 dies in the co-pack solution to make it a bidirectional switch. In case of silicon carbide MOSFETs or maybe GaN MOSFETs these days, we can put 2 MOSFETs back to back and make it a bidirectional switch. I think there have been some efforts to make it as a monolithic as well, but nothing that is commercial so far. So if you look at IGBT, because of the knee voltage and that extra voltage drop, if you put an IGBT back to back, approximately 3 volts of voltage drop is very typical. And 3 volt is a significant voltage drop for a bidirectional switch application, especially when we talk about protection switches, which have continuous current flowing through them. So that results in quite a bit of total losses, conduction losses in a bidirectional switch. Now, compared to silicon carbide MOSFET, the advantage is that obviously we can reduce the RDS on to whatever value we want, and we can keep reducing the conduction losses. But for an example, if we don't want the cost to be very high, we would end up choosing somewhere around 12 milliohm switch. For example, if we do that, then even then the losses are almost 135 watts. Obviously.
Hi.
Hi.
Sure.
Okay, so if
Sorry,
we do,
I've been muted. Sorry.
yeah, if we do, even if we, one thing to note here is that if we want a 12 milliohm SiC MOSFET bidirectional switch, obviously we'll have to choose two 6 milliohm SiC MOSFETs and put them in series. So to make a 12 milliohm bidirectional switch, we need two 6 milliohm SiC MOSFETs. There are some triacs in the market which are very low power. These are very old technology, and typically high power is not suitable for triacs. So, but I did put them here as a reference. And then there is obviously B-TRAN. So B-TRAN, there are multiple ways. There is a normally on B-TRAN, and then there's a normally off B-TRAN. And if we add the cascode MOSFET loss, the driving losses, which we'll talk about in a minute, and then the conduction losses, even then there is more than 3 times reduction in the conduction losses when using a normally off B-TRAN compared to an IGBT. So there is a significant advantage that we get with B-TRAN architecture in conduction losses. So if you look at industry, there has been a lot of effort to develop monolithic bidirectional switches. It's not just us. Transform, Navitas, and few other companies have been planning to do bidirectional GaN and bidirectional SiC, but we are yet to see a commercial device in the market. And I don't believe GaN is at 1200 volt yet. So what are the commercial applications? There is a significant change in the industry right now in the power electronics community where there are multiple applications which need bidirectional switches, and some of the new topologies have emerged as well that make use of a good bidirectional switch and enhance the system efficiency. Obviously, there is circuit protection, and we need bidirectional switches for solid-state circuit protection. The advantages of a solid-state breaker versus a mechanical breaker are evident that a solid-state breaker can break a fault in microseconds compared to milliseconds in a mechanical breaker. There is a lot of wear and tear with mechanical breakers, arcing, and that creates other issues. So solid-state circuit breaker is definitely something that is really becoming popular in the industry, and B-TRAN is definitely enabling some of that market. There is T-type inverters, Vienna rectifiers. So solar industry and EV charging rectifiers are moving towards T-type topologies because they provide a lot of advantages in system efficiency and power factor correction. So that's also one of the applications. There are matrix converters. These are not so popular in the industry right now, but with new bidirectional switches coming to the market, there is a lot of scope for single stage AC to DC, AC to AC conversion that matrix converters can enable. One of the types of matrix converters can be current source inverters, which is really good for motor drives. And there is long back, I would say, like I think before IGBTs, there was motor drives definitely used current source inverters. And now with MOSFETs and IGBTs, that has all transitioned to voltage source. But there are a lot of advantages that a current source inverter brings to the system. And it really helps with the motor life as well. So these are all a lot of different applications, and the industries are quite diverse. Like there is all the way from renewables to industrial to UPS in data centers and to EV charging. There's a wide range of markets and applications for bidirectional switches today. In fact, there is a very good article that Dr. Huber and Dr. Kohler wrote in the magazine, IEEE magazine, and I would highly recommend to look at that because he really goes in details of how bidirectional switches can help with your system efficiency. Okay. The next, we'll move on to some device test and characterization results that we have for B-TRAN and how we can design a driver for B-TRAN. So we have Gen 1 silicon in lab. That's what we are selling right now. It's a commercial product. And the results that we have are very encouraging. So on the left here on the top, you'll see that we have 25°C operation and output characteristics of the device. So VEE is our voltage drop across the device, and IEE is the current across the device. And you'll see that the current or the RDS on is obviously a function of the base current. So higher the base current we have, the lower the RDS on we can get. At the same time, the saturation is also a function of the base current. So the more base current we inject, the more current we can get out of the device. So if you look at 50 amps data here, the voltage drop is only 0.3 volt at 50 amps. So there is this significant reduction in VC on, and that is what helps us with the system efficiency and conduction losses. The device is also rated to work up to 175C, and you'll see the same graph shifted here at 175C, and you'll see that the RDS on is actually higher for higher temperature. Now, this is also important because that means that the device has positive temperature coefficient, and it's really, there is no crossover point. So IGBTs typically have a crossover point that after a certain load, that is when they become positive temperature coefficient, whereas for B-TRAN, that's not the case. So if you have base current that is controlled, all the curves shift to the right, and that means the resistance increases as the temperature increases. This data is plotted here, where I'm showing RDS on as a function of temperature, and there's a graph that it goes up, and that's a good thing. And we also have switching energy here. Generation 1 is optimized for conduction losses and not for high-speed switching, and hence there is slightly higher switching losses in Gen 1, and we expected that. We have really optimized this design for solid-state protection applications. However, we are working on Gen 2 devices, and which will be much higher switching frequency and much lower switching losses. So overall, we see the device is operating. We can operate the device up to 175C. There is no knee voltage compared to IGBT. So that means you have good light load efficiency, and your VC on is lower as you go in lower load current. The other unique thing that we see here is that the saturation current is really controlled by the base current. So if we limit, for example, the base current to 8 amps, right, the device enters the saturation at 50 amps, right? So what that means is the ability to detect overcurrent and the ability to detect short circuit current is much better, because there's a good amount of change in the voltage drop across the device, and the DSAT circuits can just be more reliable. Also, if we can limit the base current, for example, in an application, depending on how much load we want to pass through the device, that inherently provides an overcurrent protection, because if you limit the base current, the load current would be limited as well. So that was those were the characteristics actually tested in our lab on our Gen 1 device. Next, I think we should understand how do we drive this device, right? We've talked about how B-TRAN is a current-driven device, and we need to drive current into the base B1 and B2 to lower the resistance of the drift region. At the same time, we need to control the cascode FETs and we turn on and turn off the cascode FETs to control on and off of the switch. So on the left here, I'm showing a circuit that represents the on state of the device, and how we would implement that is basically shown here. So what we have done is these two low voltage cascode MOSFETs, we have built a multi-chip module, and we integrate these two MOSFETs inside our module. That also helps with the performance. If we order a discrete device, we can always do that in our PCB itself. So it's not very sensitive. To implement this circuit and to implement the driver, we have a symmetrical structure on the top and the bottom. So there is a small 1.5 volt buck converter that we have to drive current into the base. And FET Q1A and Q2A are low voltage MOSFETs that basically control the on and off of the base supply. So when we turn on Q1A or the top side FET or Q1B, we inject current into the bases B1 and B2. And at that time, Q2A and Q2B are turned off. However, when we want to turn off the device, we just stop injecting. So we turn off Q1A and Q1B, but we turn on Q2A and Q2B. So that shorts B1 to S1 and B2 to S2. And we open Q3A and Q4B. Right? So we open these two FETs as well. So essentially, to control a B-TRAN, we are controlling 3 switches on the top and 3 switches on the bottom. And these are a simple silicon MOSFET, which is a 20 volt MOSFET and can be driven by a very basic gate driver. So if you look at an overall block diagram of a driver, there is a logic controller, and this is rather simple, but we can use a small microcontroller or a small microcontroller with any additional feature that we may need. In addition to that, we have a gate driver on the top and the bottom that drives these 3 FETs. And the logic to drive these 3 FETs resides in a small logic controller. We have built this driver today using discrete components from the available in the market, and it works really well. We also have plans to make this into an ASIC, which is what we typically are used to with our gate drivers ICs on the market. So that is something we are planning in the future. So in summary, B-TRAN, for the base drive, we just use a simple buck converter, and we can have this buck converter limit the current and work in CC or CV modes to implement some more intelligence into the system. We have standard low voltage gate drivers that can be used to turn on and turn off the 3 FETs on the top and the 3 FETs on the bottom. And we drive both sides symmetrically, which simplifies the control, and there is no need to sense the direction of current or voltage. Okay. So we're moving to the last section of this presentation. Now we've talked about how the B-TRAN operates and how it is driven. We look at how we implement this in an actual application. In this case, this is a solid-state protection circuit. What are the key requirements for this application and why we should use B-TRAN? We also have some good test results and some future work that we intend to do. So overall, when you look at a solid-state protection circuit, right, there is a semiconductor device. In this case, it is B-TRAN, and it is sized to make sure that we are able to handle the load current and it is able to handle the short circuit current. In parallel, we typically use either a MOV or a snubber or both for over voltage protection. And then it communicates via a microcontroller where we can, or some controller which we can use to turn on and turn off the device. So overall, the main requirements for a solid-state protection switch would be low conduction losses. In mechanical breakers, we are used to almost no conduction losses because it's just a mechanical contact and they're all metal. But in solid state, as we move towards semiconductors, the conduction losses become an important part of selecting the power semiconductor switch. As we just looked at this, B-TRAN offers one of the lowest conduction losses compared to other bidirectional switches. And we already have a 1200 volt 4 milliohm bidirectional switch, which is state of the art. Good short circuit withstand time is another important requirement, because once these devices, these power semiconductors devices see a short circuit, they should be able to withstand it for some amount of time till the fault is cleared. IGBT is typically rated to around 8 microseconds, and B-TRAN is similar, but even better. It's 10 microsecond, and silicon carbide, which is becoming very popular, is not very good. It's 3 to 5 microseconds for a SiC, and that's mostly related to the material and its capabilities. Fast reaction time is also very important. That's one of the reasons why we would move towards solid state. And just like any other power semiconductor device, B-TRAN is also fast enough for providing good fault clearing times. Positive temperature coefficient is very important. So that allows us to parallel multiple devices and move to higher power applications. So we saw that it has positive temperature coefficient for the entire load range. So all of these features make B-TRAN very suitable for these applications. There are other advantages as well. We've been doing a lot of testing, and there's a lot of good work done by our engineering team here in understanding the device behavior, and also how we can make advantage of the unique characteristics of the device in solid state protection applications. This first one here is actually quite unique to B-TRAN. So typically what we do is we have a snubber circuit in parallel to our solid state power semiconductor switch. And the snubber has a resistor in series so that we can, limit the peak current when we are charging and discharging the cap. But the limitation of using a resistor is that the turn on and turn off are very slow, and that increases the losses. And it also adds some delay to turn off. So when we want fast reaction time, adding a resistor there would limit the reaction time. In B-TRAN, however, we recently we've discovered some unique ways to get around this. We've eliminated the resistor completely. And what that does is it really speeds up our process. So during turn on, the charging of the cap is fast. During turn off, the charging of the cap is fast. And during turn on, when we turn on B-TRAN, to limit the current, the peak current from the cap to the B-TRAN, we start B-TRAN in a high resistance mode. So for example, if we drive no current or very low current into the B-TRAN during turn on, we can really increase the resistance of B-TRAN. And once that resistance is high, we can discharge the cap through that high resistance and limit the peak current. And as it turns on, we can inject more and more base current and lower the resistance of the device. So this intelligent soft turn on that we've implemented in our reference design helps eliminate that resistor and uses B-TRAN's inherent resistor controlled properties to implement and to get around the peak current issue. Another good feature is the controllable base current and how we can control the short circuit current with this as well. Typically, silicon carbide MOSFETs and IGBTs have very high short circuit currents. And so if there is a short, until you open the switch, the short can continue for a long time and you can have very high currents pass through the device. Whereas in this case, if there is a limitation on the base current, and if we limit it to the maximum current that we want, the load current will naturally be limited. And it provides enough time to the protection circuit to kick in and open the device. In addition to that, we've spent a lot of time in doing unique packaging. Because our die is fully symmetrical on top and bottom, we understood that that's a unique advantage we have. And it also enables us to package the device and the dies symmetrically from both bottom and top. So not only do we have but double side cool packages, but it also allows for symmetrical heat conduction from top and bottom. And that is a unique advantage with B-TRAN. Typically, if we see a double-sided cool package in IGBTs or MOSFETs, they have either wire bonds on one side or a spacer on one side. That basically means that the heat that flows from the top is not the same as that heat flows from the bottom. So there's always a difference, and there is more heat that comes from the bottom than the top. Whereas in B-TRAN, the heat flow is symmetrical. So you can get the most out of your heat sink design and really get the more power dense solution that we want in this case. Okay. Here is a quick example of our reference design. We did a reference design and tested the breaker operation across our device. So first of all, we packaged our TO264 device with double-sided heatsink. So we took a standard TO264 heatsink and added a front plate and a heatsink to it and sandwiched the device between it. Now, what that enabled us is just get more current out of the same device because the device is capable, but in the same volume, we were able to get more power. We also tested up to 200 amps of braking in a single device, and this is at 400 volt. And as you can see on the left graph here, our current protection or the shunt resistor protection is set to about 180 amps, and it trips at 180 amps, and it moves very fast. In less than 45 nanoseconds, we turn off the cascode FET, which starts the turning off process of the device. Now, because you have some fault inductance, loop inductance, and snubber capacitance, the device turns off, but the current takes time to clear the fault. And even then, it takes about just 6 microseconds to completely clear the fault and take the current from 200 amps down to 0 amps. This is also pretty good if you look at other solid-state breaker performances. The fault clearing time is really a function of how much loop inductance we have and how much snubber capacitance we're using, and also what is the total fault clearing current. In terms of thermal savings, I think I was just talking about this. In that small heatsink that we just showed, we were able to dissipate almost 50 watts of power through B-TRAN double-sided cooled device. And that's with a very small, like 200 CFM airflow. Now, if you look at a conventional single-side cooled package and a single-side cooled heatsink like what we have there, this is almost 40% more power dissipation compared to a single-side cooled device. The data sheet of this heatsink is given here, and you'll see that for this heatsink, they typically recommend up to 10 watts of power dissipation. And for higher power dissipation, you may need more and more airflow, and that increases the cost. So for 200 CFM, they would typically rate this at 10 watts, 20 watts, whereas we are able to get up to 50 watts out of this. For 50 watts, as you can imagine, like for us, including the driving losses and everything, we were able to get more than 60 amps of continuous current through this device. Okay, so now what we are planning to do is we want to address this concept, and we are working on a high current, high power breaker, which will be using our multi-chip B-TRAN module. SimCool is a product that we've launched, and it's a multi-chip B-TRAN module with 4 B-TRANs in parallel, and it also has cascode MOSFETs co-packed inside in a very small double-sided cooled package. This package size is standard in the industry. It is similar to the double-sided cooled packages used in automotive industry by multiple vendors like onsemi, Infineon, but we package a lot more die inside, and the power rating is also pretty good. For continuous rating, we have right now rated up to 160 amps, but this is quite conservative. As we test more and more, we see that this easily can do up to 400 amps. And we are working on a reference design that will help us test this. And we can do up to almost 600 amps of braking current, or short circuit current using this module. We're also working on next generation B-TRAN, and that will help improve the performance even further. Okay, thank you.
Thank you very much, Mudit, for the nice presentation, and thank you everybody for joining today's webinar. So as a reminder, you can type the questions in the chat and I'll call on you to unmute yourself. And to head off the question, a PDF of the presentation will be shared with all registered attendees within a week. So by the end of the week, you'll have the PDF. Maybe a first question to get things started from me. So you mentioned that some of the devices were being manufactured now. I was just wondering where you were at. Are they available for purchase for people looking to evaluate them, or kind of where you're at in the kind of commercialization side?
Yeah, absolutely. So we have devices available. Yes, we have discrete device available for purchase. We have the SimPool module that we just showed. That is also available for purchase. We have the reference design. So if anybody wants to evaluate the breaker performance, we can just sample the reference design, and that is also available to purchase. We have drivers as well. So yeah, definitely feel free to reach out to me and we can help you with any of the needs. It's not available on Mouser or DigiKey as of now. We are going through our own distributor partners, but if you contact us, we'll definitely help you with the samples, and it's all available for purchase. Yeah.
Okay, cool. Thank you. Neil, could you go ahead and unmute yourself, or if not, I can read the question aloud. So Neil Ormos had the question, when using the cascode MOSFETs on either side of the B-TRAN device, how do you ensure that the voltage to which the MOSFETs are exposed is low? For example, 60 volts, as you mentioned, and not some large fraction of the 1200 volt rail-to-rail supply.
Yeah, that's a really good question. And that is dependent on really the device design. So our device is designed in a way that allows for such operations. So if you look at this structure here, when we open the cascode MOSFETs, when the N rises 40 volt above P, the region is already depleted. So we have the diode already in complete blocking stage, this diode and this diode. So this PN diode is also blocking and this diode is also blocking. So yeah, it never goes above 40 because the B-TRAN the junctions are depleted.
Okay, interesting. Yeah, thank you. And then Grant Piddle had a question. So the first one, the recording will be made available to attendees. And his question for you, Mudit, is there anything on the roadmap for normally on devices?
We already have a discrete device, and that is a normally on device. That's a TO264 package that we showed in the evaluation. That's normally on. Yeah. We can look at other. If we have like more interest in normally on devices, we can consider some custom devices as well. Yeah. We have some flexibility in packaging them, basically.
Okay, interesting. Yeah, thank you. I had another question. So it's very interesting thinking about the protection device application where the metrics are very high, like braking current and things like that. But then there's also the switching application, like a motor drive or something like that. Are you anticipating like different devices targeting the different applications, or kind of the same devices? Like you could use an IGBT anywhere, kind of thing.
Right. No, we are definitely targeting those applications as well. The architecture will remain the same mostly. What we are doing is we are optimizing the performance in a way that suits motor drives a lot more. Currently, we are we are working on some concepts. Actually, we have current engagements that are our customers are looking at motor drives already, and our Gen 2 device is really suited for motor drive applications.
Okay, interesting. Yeah, I saw the public announcement with Stellantis, so that was that's interesting. So
exactly. Yeah.
Thank you. Jay, I'll ask you to unmute yourself.
Hi, these are fascinating. I guess I'm not clear exactly from the two different pictures how your gate driver controls the B-TRAN and cast codes when maybe S1 is 800 volts, maybe S2 is 0. Is it part of it floating? And how do you keep the cast code and other control FETs from seeing that high voltage?
Okay. Yeah, so the gate driver is floating. So if I look at the gate driver structure here, you'll see that this part of the circuit, the top side FETs, they're all referenced to S1, whereas the bottom side FETs are referenced to S2. And these are all referenced via floating supply. So this 1.5 volt is a floating supply. So what we need is just a 20 volt FET here and here. So B2 with reference to S2 is just 40 volts. It will never go above 40 volts because that's the cell architecture that we've developed here. So between B2 and E2, there is always 40 volt. But between S2 and B2, we only have 1.5 volts. So this FET here is really just blocking 2 volts that we want to drive the base with.
So to say to drive Q1, so your driver has a P channel FET to turn that on and off? And then
so
for Q1, you'd have N channel FETs driving them on and off?
Correct. A typical gate driver, which is a CMOS, like a PMOS and an NMOS pair, can drive these two. Just like a standard silicon MOSFET gate driver can drive this FET. The only thing is that FET needs to have a reference of S2 because the source of the MOSFET is referenced to S2.
Right.
So
Okay.
the gate to source, we need to make sure that the gate to source is 5 volts, right?
Right.
So we have two floating supplies, one on S1 and one on S2. And those floating supplies are isolated. So if you look at our gate driver here, so we have one S1 floating supply on the top, and then one S2 floating supply on the bottom. So all the digital signals can be referenced to this.
Oh, okay. Okay, I see. All right, thank you very much. Yes. And you say there's an eval board for these to experiment with?
Yes.
And that's on your website?
It's not on our website yet. Right now we are going through, but there is information on website on how to contact us. But if you contact us directly or me, I can help you with the sampling. We've not made that public yet. Yeah.
Okay, and then with all these gate driver, with all these transistors, how do you maintain or attain the 200 nanosecond switch time? It seems like there's a lot of gate capacitance there that you need to overcome.
Yeah, because these are very low voltage MOSFETs, Jay, like 20 volt and 60 volts, they turn off in tens of nanoseconds. So even though we are driving a 1200 volt device, we are really just turning off a 60 volt MOSFET.
Okay. Wow, that's really neat. Well, thank you very much.
Mm-hmm.
Thank you. So Neil had a question as well. For the normally on device, what fraction of full device current is passed when zero base current is supplied?
Okay, so when there is zero base current, that's very interesting because the device is a resistor. It's just a pure resistor, and the resistance is like 2 ohms. So you can pass as much current, but the resistance, the voltage drop just keeps increasing. So at some point, there will be a thermal limit and there will be too much voltage drops because it's a 2 ohm resistor.
Yeah, that's interesting to think about.
Yeah.
Thank you. And then Daniel Peters had a question. When will these be available at Mauser or DigiKey?
We're working on that because this is a unique architecture. What we want is our customers to engage with us because there is some sort of information needed to be transferred, and we want to make sure that they are able to use it in the right way. And as we mature enough that we have products which are more user-friendly, and let's say people know more about this, we can, get this out on Mauser as well. And that is not very far away, but for now, we are making sure that we are able to educate our customers in the right way, and they're able to help them. Yeah.
Okay, interesting. Yeah, thank you. So I think I just have maybe one more question. So kind of thinking about different device technologies, like silicon carbide and GaN, like one of the challenges in adopting, for example, silicon carbide was, it switched so much faster than people were used to. So you have your layout with an IGBT, and you put in silicon carbide, and you have all kinds of issues, and maybe a similar story with GaN. It's pretty sensitive to the gate voltage. If it's too high, you're liable to blow your device, kind of thing. In terms of thinking about applying these devices, I don't know. It seems to me like there's a lot of very good benefits. Is there a tip or trick you have for people thinking about applying it? Maybe your one key thing to think about.
Yeah. So when we talk about switching circuits, let me talk a little bit about switching applications. So we've talked a lot about conduction losses, and switching losses are also a significant part in a switching converter. And you're absolutely right that with silicon carbide and wide bandgap devices, we did not necessarily need such high switching speeds in all our applications. Some applications, yeah, we definitely needed them. But the market is just reacting, and the systems engineers are just reacting to devices they have available for them. B-TRAN is not going to be a silicon carbide because it's a silicon device. I mean, the architecture is different, but the device and the silicon and the processes are very similar to IGBT. So what we've done is, what we see is, especially in motor drive applications, when we are working on our Gen 2 device, for example, we've optimized the switching performance to the level that is friendly to the motor. And we don't need to go any higher than that because really there is no need. But if we look at the loss breakdown in a motor drive application, a significant portion comes from conduction losses because there is high current and there is also low frequency. I mean, motor drives don't operate at very high frequency, not like hundreds of kilohertz or megahertz, right? It's mostly tens of kilohertz. And when we look at that sort of frequency range, B-TRAN really shines because of our low conduction losses. And we keep the switching frequency to a level where it would be friendly to the motor. So very similar to IGBT. So that's where we are with our switching converter applications. I would say by next year, we would see maybe we can do a talk on switching converters and our Gen 2 device and how it performs. But that's in development right now. Yeah.
Okay, very interesting. Yeah, thank you very much for highlighting this technology. So with that, I'd like to thank you again for the very nice presentation, and thank you everybody for joining. You'll see I'll follow up to all of the attendees. I'll send out your email address in case people are interested in contacting you for samples, additional information, as well as the slides and the link to the recording. So thank you again. I really appreciate your time.
Thank you, John, and thank you, everyone. And please, let me know if there is any questions. Happy to answer.
Great. Thank you so much.
Thanks.